Okay, thank you so much for being here. I know it's late, so we'll get started here and get you guys out on time for some dinner. For most of human history, a community's first warning about a deadly earthquake would be the moment that the ground started shaking beneath their feet. This would mean that people had no time to respond to that earthquake, find shelter, and make themselves safe, leading to massive damage and significant loss of life. Thankfully, today, due to advances in seismic and geodetic sciences, we are now able to detect earthquakes happening in real time and send life-saving alerts to those who will be impacted before the shaking arrives. Today, you'll hear from the EarthScope Consortium, an organization responsible for measuring and reporting the movement of the Earth's crust, helping power that earthquake early warning system. I'm Matt Bollinger. I am a senior solutions architect here at AWS on our nonprofit research team, and I'm joined by Alex Hamilton, a senior cloud architect at the EarthScope Consortium, and he'll be telling us a little bit about who EarthScope is, what they do, and then he'll give us a small science lesson into earthquakes and earthquake detection and the importance of what they do in powering that system. Then he'll go into how they've built that system on AWS, focusing on their real-time ingestion pipeline and processing, going into their observability and archival systems. And then I'll come back to close this out, highlighting some of the really non-technical things that EarthScope has done that made them successful on AWS and how you can replicate those things within your own organization. And so with that, Alex, over to you.
All right, thanks for that introduction, Matt. So EarthScope Consortium is a nonprofit organization that's funded by the National Science Foundation, the U.S. Geological Survey, or USGS, and NASA. And we operate two major facility awards on behalf of the National Science Foundation, one for the scientific discipline of geodesy and the other for seismology. And our ultimate goal is to advance human understanding of the Earth and its physical systems by democratizing access to geophysical data and enabling transformative research. EarthScope is realizing a vision for integrating many geophysical scientific disciplines. Our core data sets are geodesy, seismology, and INSAR, but we collect and archive data for many more. For the purposes of this talk, we're going to primarily focus on the scientific discipline of geodesy, and furthermore, just a single instrument for measuring geodesy, Global Navigation Satellite Systems, or GNSS. But first, I want us all to have an understanding of what geodesy is. Geodesy is the science of measuring and studying the Earth's shape, its gravity, its orientation in space, and how all of these properties change over time. Put simply, we're looking at where things are, where they've been, and where they're going, both in extremely long time scales, such as continental drift or the movement of glaciers, and in extremely short time scales, like positioning for autonomous vehicles. And it's a little bit ironic that many folks have a basic understanding, or at least are familiar with the idea of seismology, even though many folks who are not seismologists don't use seismology in their day-to-day lives. Conversely, most people have never even heard of geodesy, even though many of us are impacted by it multiple times a day. For example, every time you use the GPS on your phone to navigate from point A to point B, you're leveraging geodesy. Another area that we use geodesy today is in the USGS ShakeAlert earthquake early warning system. The goal of ShakeAlert and earthquake early warning systems in general is to provide the public and automated systems with advance warning that an earthquake has occurred and that damaging shaking will be arriving imminently. Ideally, we'd be able to provide minutes of advance warning, but even 30 seconds can be enough time to mitigate absolute disaster. Think about the impact of stopping trains or shutting off gas lines in nuclear reactors or even pausing surgeries. While earthquake prediction is not currently possible, the actions that we can take today with modern earthquake early warning systems have the potential to save many lives. The way that earthquake early warning systems function is by distributing tons of geophysical instrumentation around the world. And when an earthquake occurs, the physical waves that are propagating through the earth can be observed by these instruments. And different instruments are looking at different characteristics of the earthquake. Fortunately, these physical waves that are propagating are significantly slower than our modern electronics and communication systems. So we're able to measure the earthquake out in the field, transmit that data back to our processing centers, determine that an earthquake has occurred, and then issue an alert to the public. Now, historically, earthquake early warning systems have been almost exclusively reliant on seismic instrumentation. And while seismic instruments are really good at analyzing many characteristics of an earthquake, one of the areas in particular that they struggle is to accurately estimate the magnitude of large earthquakes in real time. This is because during large earthquakes, seismic instruments tend to saturate, meaning that they max out on the scale that they're measuring. And when this occurs, they often end up underestimating the magnitude of the earthquake, which means that any alerts that are sent out to the public are underrepresenting that earthquake, and any precautionary measures taken by the public or automated systems is disproportionate in comparison to the amount of danger and destruction that's actually headed their way. So we have this need for a complementary data set. One of the prime examples of this shortcoming was the 2011 magnitude 9 earthquake that hit about 100 kilometers off the eastern coast of Japan. At the time, Japan had the most advanced earthquake early warning system in the world, but it was almost exclusively reliant on seismic instrumentation. The plot here on the left shows the magnitude estimates issued by that early warning system over the first hour after the earthquake occurred. You can see during the first 20 minutes, the magnitude estimates ramp up from below magnitude 7 to a 7.3, then 7.9, and finally up to a magnitude 9 after 20 minutes. Now, 20 minutes may sound like a relatively reasonable amount of time. However, that vertical blue line at 15 minutes is showing the tsunami arrival time at the coast. This figure in the middle is showing the tsunami hazard that was issued based off of the magnitude 7.9 estimate. You can see that relatively short section of coastline in red where the tsunami was estimated to be greater than 3 meters, while the majority of the coastline was expecting less than half a meter of tsunami. Well, the bleak reality of the situation was that almost the entire eastern coast of Japan would see a tsunami greater than 3 meters, and the tsunami was actually measured in some areas by tide gauges at greater than 9 meters. This event, and others just like it, clearly demonstrate the need for a complementary data set for looking at different characteristics of the earthquakes than what seismic instruments are looking at. And in no way is this to replace seismic instrumentation. We're trying to augment and enhance our real-time understanding of what's unfolding. This complementary data set comes to us in the form of Global Navigation Satellite Systems, or GNSS. GNSS are constellations of satellites orbiting the Earth that are constantly broadcasting signals down to the surface, where we have GNSS receivers, or stations as we commonly call them, represented as the red dot in this animation. These stations are listening for those signals sent by the satellites, and when they receive those signals, they use the speed of light and knowledge of the makeup of our atmosphere to determine, to a very accurate degree, the distance between an individual satellite and this station. And they're simultaneously doing this for every GNSS satellite that they're able to see. Then, with a bunch of complex math that we'll just hand wave past for this presentation, they're able to determine the latitude and longitude and height of this instrument in real time to centimeter accuracy. This is what we call a precise point position, or PPP. And PPP is significant for the purpose of earthquake early warning because during large earthquakes, we actually see deformation and the displacement at the surface of the Earth that's at the scale of meters. Furthermore, what's been proven is that there's an empirical relationship between the maximum amount of displacement that we see at those stations and the magnitude of the earthquake. So using this peak ground displacement, or PGD measurement, we're able to back out the magnitude of the earthquake to within 0.2 or even 0.1 magnitude units within seconds of with this displacement occurring. This peak ground displacement measurement is what's powering large earthquake estimation in ShakeAlert today. With all this in mind, let's step back to that magnitude 9 earthquake that hit Japan. Japan also has an extensive network of GNSS instrumentation. But at the time of this earthquake, they were not part of the earthquake early warning system. However, this animation that I'll play here shortly is going to show the actual displacements that were observed at all of these GNSS sites as the earthquake was unfolding. On the left side, we're going to see the horizontal displacement measured in meters, and on the right side, the vertical displacement. The red star that's going to pop up here shortly is the epicenter of the earthquake. Within 60 seconds of the earthquake starting, we see that the damaging shaking has reached the coastline and the displacement begins. Not even 1 minute after that, and we can see that a significant portion of the mainland of Japan has shifted eastward 10 to 15 feet. If GNSS had been part of the earthquake early warning system, we would have known that this was a magnitude 9 earthquake within 2 minutes of the earthquake occurring. This second aftershock down below here is a magnitude 7.9. And this is illustrating the exponential difference between a magnitude 9 event and a magnitude 7.9 event. Now, if you've never experienced an earthquake before, it can be hard to fathom the size and the scale of these events. Let's just try to imagine all of us here today, or the entire Vegas Strip, or actually the entire landmass of the state of Nevada, just shifting 10 to 15 feet over a timeline measured in seconds. While this is not going to occur here in Nevada, we fully expect that an earthquake just like this one is going to hit the Pacific Northwest, and we expect it to be a similar magnitude as this event. This is why it's imperative that GNSS data be incorporated into the earthquake early warning system. All right, so now that we've established a foundation of the science involved in earthquake early warning, let's move into a technical discussion of the system that EarthScope has built out in AWS for handling real-time GNSS data. EarthScope's purview extends from all the way at the edge in terms of the physical instrumentation through data collection and production of those precise point positions and peak ground displacement measurements, and then the handoff of that data to the USGS. It's important to pause here and say that EarthScope is not responsible for issuing alerts. That is the USGS's responsibility. However, EarthScope's responsibility does not end at that point. We're also responsible for providing detailed visibility into the behavior of this system. And our core responsibility in the fulfillment of our award from the National Science Foundation is the long-term archival and distribution of this data to the scientific community. Now, before we dive in here, I want to call out that while a lot of the data that we're moving around is certainly very specific to our use case, the software and the architectural problems that we're addressing are far from unique. And many of you here today are probably facing similar problems in your own work. For example, our fleet of GNSS stations that we're collecting data from. This basically boils down to an IoT data ingestion problem. Then computing precise point positions and peak ground displacement measurements from the raw data. This is just stream processing. Then we've deployed this distributed system in the cloud. We have to have visibility into what's going on in there. And then fourth, we have to archive all of this data so that our data scientists can make use of this data and extract meaning from it. It just happens to be that our data scientists are the research community of the world. Let's start at the top of this table and work our way through all of these challenges and talk about how EarthScope has addressed them. Our GNSS network started off back in 1984 when EarthScope received a $1 million grant to purchase 4 of the very first commercially available GPS receivers. It's pretty hard to imagine that these things used to cost $250,000 a piece, in 1984 dollars nonetheless, when all of us here today have one of them in our pocket, and many of us have one on our wrist as well. As technology evolved and these receivers and instruments came down in price, EarthScope grew to manage a pool of these instruments that researchers could borrow for their own temporary experiments. They would come to EarthScope and borrow these instruments, take them out in the field, set them up, and leave them for a season or however long their experiment required, and then they would go back to collect the data and the instrument. Fast forward to today, and EarthScope collects GNSS data from thousands of instruments around the world. Furthermore, we operate 1,100 of these stations around North America and the Caribbean on behalf of the National Science Foundation, meaning that EarthScope also employs a team of field engineers responsible for going out into these remote areas and installing and maintaining these instruments. I mean, think about all the work involved in traveling to the edges of the Earth to replace batteries and solar panels and upgrade communication systems. Over 90% of these stations are streaming data to us in real time at 1 hertz. The ones that aren't are in extremely remote areas like the Arctic and the Antarctic, where we face pretty harsh constraints in terms of conditions and the power, the amount of power that's available and the communication services that are available. For the stations that are streaming real-time data, though, we had to build out a real-time stream processing system to handle this workload. And you might recall that that's the second row in our table of common patterns that we have to address. Our stream processing system is built pretty much exclusively out of these two managed services: managed streaming for Kafka, or MSK, and Elastic Container Service, ECS. Kafka is the central nervous system of our real-time platform. All of our real-time streaming data flows through Kafka. On the other hand, our stream processing applications are packaged up as containers, and we use ECS to deploy and manage their life cycles. We especially love using ECS's Fargate capacity provider so that we can focus exclusively on our business logic and not have to worry about managing compute. We just tell ECS how many CPUs and how much memory our application requires, and ECS handles the rest for us. Here's a simplified look at our stream processing topology. On the left there are the GNSS stations, and then our first ECS service here is solely responsible for ingress. This is the entity that's actually reaching out to the instruments and pulling their data into our cloud, where the data is published to Kafka topics. Next, we have another ECS service that's responsible for distributing this data to the USGS, to our ShakeAlert processing centers. These are our partners who are responsible for actually turning the raw data, those individual range measurements between every satellite in the station, and turning that data into precise point positions, or PPP. Then the ingress processor, or service, is additionally responsible for reaching out to our ShakeAlert processing centers and pulling that PPP data back into our cloud and publishing it to more Kafka topics. Where we have a third ECS service that's doing a little bit of stateless processing to normalize various different position formats into a common shape, and then also performing some stateful processing, looking at sliding 2-minute windows and extracting the peak ground displacement that we observe during those windows. So we're looking here at the topology of our streaming data flow, and it flows more or less left to right through this diagram. Let's now pick one of these ECS services and look orthogonally at a cross-section and dig into the architectural benefits that we get from using these two managed services. These benefits come in 3 broad categories. The first is horizontal scalability, fault tolerance, high availability. The second is the decoupling of our control plane from our data plane. And third is the extensibility and flexibility that we get with these services. This diagram shows the physical distribution of our computational resources across a region's availability zones. And we're looking at this distribution in terms of the logical abstractions that we interact with when we use these managed services. So up top here, we have our ECS service. This abstraction is responsible for running multiple instances of our application, or ECS tasks, and distributing them across the region's availability zones. This ensures geographic redundancy in the unlikely event of an AZ outage, And furthermore, the service is also responsible for checking on the health of our individual ECS tasks and containers, and restarting them or spawning new ones should any issues arise. It's also monitoring custom metrics to scale in and out in response to changes in our workload. Down below here, we've got our MSK Kafka cluster. It takes care of a lot of the same geographic redundancy and high availability problems that the ECS service is addressing, but for our Kafka cluster. MSK, as a managed service, is taking care of provisioning these brokers for us and distributing them across the availability zones in the region, and then managing their life cycles, so we don't have to worry about that. The key to horizontally scaling our streaming workload, though, since we need to do stateful processing, lies in Kafka's simple yet extremely effective topic partitioning design. Topics consist of a configurable number of partitions, and when messages are produced to Kafka, they are assigned to partitions predictably based off of a hash of the message's key. We use our station IDs as this message key, and this ensures that all of the data from an individual station ends up in the same physical partition. Next, all of our ECS tasks in an ECS service connect to the Kafka cluster and read from that topic as members of the same consumer group. This ensures, thanks to Kafka's consumer protocol, that the partitions are distributed as close to evenly as possible across the members of the consumer group, across our available compute as we've scaled out here. This is the key functionality that allows us to perform stateful stream processing, because all of the data from an individual station is going to the same compute that's processing that data. Furthermore, the Kafka consumer protocol maintains heartbeats between the members of the consumer group and the Kafka cluster. So if any of these heartbeats stop, the Kafka cluster can perform what's called rebalancing and distribute the partitions across the remaining instances in the service. This also happens in reverse. Once ECS has respawned these tasks, or if we're simply scaling out our consumer group, then Kafka will once again rebalance and distribute those partitions as close to evenly as possible across the available compute. So now that we've explored how MSK and ECS facilitate resilient and scalable stream processing in our data plane, let's shift focus to our control plane. Everything we've been discussing up to this point has been about our data plane. That's where the primary functionality of our business logic occurs. The control plane, on the other hand, serves as the administrative backbone to this system, providing the tools and interfaces that our operators need to manage configurations and ultimately steer this ship. Let's dive in here into how we've achieved this decoupling and how it enhances our overall architecture. Here's our streaming topology once again. And up top there is our data plane that we discussed previously. Our control plane here now gets dropped into this diagram as just more ECS services that are managing their own stateful storage. The key here to achieving the decoupling is that these configuration services are replicating the current value of their configurations immediately upon change into compacted Kafka topics. Compacted Kafka topics down in the data plane behave like tables. And thanks to Kafka's topic partitioning design, as long as we have the same number of partitions in our configuration compacted topic as we do in our data streaming topic, we're guaranteed that the configuration for station A is co-located with the data that's streaming through for station A. So we're able to still have our scalable stream processing that's stateful and immediately apply changes down into the data plane from our control plane. Furthermore, the data plane is never interacting with the control plane. There's a one-way flow of configuration and information from an operator into the control plane and then down into the data plane. Because of this, we have much less stringent uptime requirements for our control plane. The control plane could partially or even completely go down, and the data plane would never know the difference, because a lack of change in the configuration is a perfectly valid state for the data plane to be in. In fact, that's the normal state for it. These configurations aren't changing all that often. This also simplifies a multi-region deployment for us because only our data plane needs to run multi-region. We can simply replicate the configuration topics into the other regions' Kafka clusters, and our control plane can remain exclusively in our primary region. Now let's explore how this architecture also enables extensibility and flexibility. By leveraging the MSK and ECS combination, we can seamlessly introduce new functionality into our system, and we can provide a consistent developer experience for our engineers and our data scientists. As we've moved through our solution, we've simply been extending the system. At no point have we had to go back to the drawing board and refactor here. We're just adding new functionality by deploying more ECS services that are either consuming from Kafka topics, producing the Kafka topics, or both. Then, this common technology stack also provides a consistent developer experience for our engineers. Many of them move around between different projects and different data pipelines, and having this common foundation in the technology stack allows them to just focus on the business logic changes as they're moving between these different data pipelines. They're familiar with ECS, they're familiar with MSK, so they can just immediately be productive in those other projects. Furthermore, it's really easy to experiment with new stream processing techniques and technologies and new data products because we can just package up those applications as containers and chuck them out into Fargate and let them do their thing. In summary, ECS and Kafka have made it relatively straightforward for us to build out a resilient, yet flexible foundation for our complex stream processing needs. If we think back to our table of common patterns now that we started off addressing, we've now addressed the first two. And the next one, or the third one, is observability. It is critical that all of the positions and peak ground displacement measurements that we deliver to the USGS are accurate and timely. So we need to ensure that the system is running correctly. Observability for us is not only monitoring the health of the system, but also the validity and the characteristics of the data that's flowing through it. At EarthScope, we've leaned heavily into the AWS flavor of the open source observability stack. This means that we use AWS distro for OpenTelemetry, or the ADOT collector, in a sidecar configuration with all of our ECS tasks to collect custom metrics, traces, and logs. The ADOT collector then sends custom metrics to Amazon Managed Service for Prometheus and traces to AWS X-Ray. Then all of our application logs flow directly out of ECS into CloudWatch. And we pull together all of these observability signals into single pane of glass dashboards for our operators using Amazon Managed Grafana. This comprehensive approach to observability provides us with the ability to monitor both the health of the system along with summary level characteristics of the underlying scientific data. Again, this new observability functionality is simply dropped into our architecture in a purely additive way. No refactoring necessary. Furthermore, we use CDK to deploy all of our applications, and our shared CDK library provided by our cloud enablement team takes care of injecting this ADOT collector into all of our ECS tasks and configuring it to send those observability signals to the appropriate data stores. So our application developers don't have to worry about that piece. Now in the bottom right of our diagram here, we've also added our operators where they're interacting with Amazon Managed Grafana. As the operations of this system matured, we discovered that those operators additionally wanted visibility into the full resolution of the time series data that was flowing through the system. And while we very successfully use ADOT and Prometheus to look at summary level information of these data, it just isn't the right tool set for looking at the full resolution data in an ad hoc manner, because we have to pre-instrument our applications to produce specific metrics. For this new use case, we really needed a purpose-built time series database. We worked with our AWS team to find Amazon TimeStream for live analytics to be a near-perfect drop-in solution. We love that TimeStream is serverless and that it has multiple storage tiers with independently configurable retention settings, so that the most recent data can stay in a high-performance memory tier that automatically fall off into a more cost-effective magnetic tier. The magic here is that TimeStream facilitates querying across both of these storage tiers seamlessly with a familiar SQL syntax. A bonus feature is that we can use TimeStream's scheduled queries functionality to perform regular rollups and aggregations of these data, which end up in their own TimeStream tables with their own configured retention settings. And for these much lower fidelity or frequent data, we're able to keep them in that lower storage tier indefinitely while still remaining cost-effective. And believe it or not, all of this is just accomplished by adding yet another ECS service that's consuming from Kafka, but this time it's writing to TimeStream. Amazon Managed Grafana has native support for querying TimeStream, so now we can provide extremely detailed dashboards for our operators. Here's a glimpse at our overview dashboard that provides a quick insight into the overall health of our network. It makes it pretty easy to see trends such as latency and completeness across our entire fleet of stations, while also immediately making it obvious which stations are experiencing issues at that point in time. Then, operators can dive into an individual station's dashboard and look at the full resolution 1 Hz data coming out of that instrument, and even issue ad hoc queries against the TimeStream tables if they would like. So in summary, TimeStream is providing short-term to medium-term storage for our full resolution data, primarily for the purpose of visualization for our operators. However, those data eventually fall off our configured retention windows, and then we move that data into our long-term archive. And that is the fourth and final row in our table of common patterns. Again, our core responsibility in the fulfillment of our award from the National Science Foundation, and ultimately our duty to the scientific community, is the long-term archival and preservation of all of this scientific data. All this data eventually lands in S3, where we leverage intelligent tiering to save upwards of 70% on our storage bill for data that are accessed infrequently, while still retaining instantaneous access to those objects. This is fantastic for our dataset in particular because there's a strong recency bias. Not only is the newer data more recent, but as you can probably imagine, scientific instrumentation has improved dramatically over the past 40 years. And it's done so in two major ways that impact us. First is that the instruments are recording in higher and higher resolutions, so there's more data coming out of individual instruments. Second is that instruments have become cheaper, so there's more instruments. Both of these factors compound and result in this exponential growth in the amount of data that we collect and archive. We're on track to cross the 2 petabyte mark by the end of this year, just in terms of pure scientific observations. And this final addition to our diagram here should come as no surprise to those of you who've been following along. We've added yet another ECS service that's consuming from Kafka, but this time writing to S3. And this is where our scientific community is able to retrieve that data. So, up to this point, we've explored the science behind earthquake early warning and the technical architecture that powers our system, diving deep into the components and how they work together to facilitate scalability, resiliency, and flexibility. Now let's shift gears here and explore the impact of this system and what it's allowed us to accomplish. The first impact is on ShakeAlert. Thanks to the integration of GNSS data, the USGS is now prepared to accurately estimate the magnitude of large earthquakes in the US in real time. As we discussed early on, this can have a significant impact on reducing the loss of life and the damage that's experienced during these large events. The second impact is that of this technical foundation we've built. The combination of MSK and ECS for stream processing provide horizontal scalability and fault tolerance. Our serverless TimeStream tables facilitate flexible and responsive querying over our real-time data within less than a second of it being written to those tables. Then S3 provides affordable and extremely durable long-term storage for these data. And we use the same technology suite for all of our different streaming data pipelines, so we're able to reap these benefits tenfold. The third impact is the impact on EarthScope from moving these workloads into AWS. We've run our own on-prem data centers for the past 40 years, so we know a thing or two when it comes to the following. We could never achieve this level of reliability and durability for these workloads in our on-prem facilities as what we can using managed services in AWS. Nor do we even want to try to do that. Look, ultimately, we care about the science and we want to focus on the science, and that's what these managed services allow us to do. And speaking of the science, these data entrusted to us represent a 40-year accumulation of observations that tell the story of our changing planet. This is an absolutely irreplaceable and priceless data set. Where else would you rather store this data than S3 with its 11 nines of durability? I know that I personally sleep better at night knowing that this data is never going anywhere. And finally, I'd like to take a moment to look forward at a few of the exciting things that EarthScope is working on. For earthquake early warning, there's many exciting developments coming around the corner, but we'll just touch on a couple here. One of these is a new, higher fidelity GNSS data product that is more sensitive to movement than precise point positioning. We're running this product internally, and we're able to clearly see earthquakes down to around magnitude 4.8, while simultaneously experiencing lower latency and consuming fewer computational resources. Another exciting development is the application of modern machine learning techniques to the problem of earthquake detection. We've done a little bit of experimenting here as well by training a SageMaker inference endpoint and then using an ECS service to perform real-time feature extraction and hit that endpoint. Next, for our scientific community, we're excited to be rolling out a Jupyter Hub data science platform with our partners at 2i2c that will enable researchers to bring their experiments adjacent to our data set and leverage free compute funded by the National Science Foundation. We've already run a few short courses in this Jupyter Hub environment, and we're excited about the capabilities that we plan to add here. And then finally, perhaps the most exciting development here is the ability for researchers to analyze our entire archive. Previously, this just has not been possible. It is very difficult to move around 2 petabytes of data on a whim, as a researcher might desire it. Not only is it hard to store that much data, but our on-prem facilities just did not have the capacity to provide that level of access, despite many researchers wanting it. They might as well have been trying to drink the ocean through a straw. However, now that these data reside in S3, they can bring their experiments, and more importantly, their compute, adjacent to our data set and analyze the entire archive. We fully expect that there will be multiple career-defining academic papers that come out of these sort of large-scale experiments over our entire archive. And we're super excited to be handing over the keys very shortly to the first research group that's going to be running one of these large-scale machine learning experiments over our entire seismic archive. Do you remember early on when we first discussed earthquake early warning? I said that earthquake prediction is not currently possible. Well, maybe one day it will be. This unfettered access to the entire archive is a critical milestone in enabling that sort of truly transformative geophysical research. And with that hopeful look into the future, I want to thank all of you here today, and I want to thank my colleagues at EarthScope who have allowed me to present all of this work on their behalf. Thank you. Back over to you, Matt.
Thank you, Alex. It's been really incredible and humbling to watch the change that's happened within EarthScope over the past 3 years and what you've been able to build and accomplish. And I want to highlight that point for everyone else that it has been a 3-year journey for EarthScope. This kind of organizational transformation doesn't happen overnight. It doesn't happen in a vacuum. It's really a journey that they've gone on to build all of this incredible stuff. And for you and your own organizations, it's important to remember that it is going to be a journey. So some things that you can keep in mind on your own if you're just starting out or halfway through or just as far as EarthScope is that when you are starting and you're trying new things, it's really important to start small. With EarthScope, we started with very tangible, self-contained proof of concepts that they were able to quickly build and iterate on to start building that experience and building up their, the entire pipeline that we looked at on AWS. And so by starting small, you're able to fully encapsulate and start with something that says, hey, I know that I am able to have this workload, try it out, experiment, and then once I have gotten that first win, start to iterate on top of it and say, now that I've got my first win, let me get my second win, my third win, my fourth, and slowly build up over time. Some of that MSK and ECS pipeline that Alex was talking about was that exact same methodology. Let's build that first ECS task. Okay, cool, now we have this, let's build the second task. And going through that small iterative process allows you to really experiment with your workload and learn what is going to make the most sense. Something Alex talked about was finding time stream as a solution for a very specific problem came from that kind of experimentation of looking out across all of AWS, the entire service catalog, and finding what is really going to meet our need for this specific use case. And then through those experiments, being able to think big, like Alex was just talking about, with the full archive analysis, with the machine learning on top of it, all of that really big. This wasn't possible on-prem, but it can now be possible within AWS. Taking that time to say, what can we actually do now that we have all of this new technology at our fingertips, and what can be possible for our researchers, for our constituencies, whatever that mission may be for you. Some of the things that Alex really was highlighting is those common patterns that they were able to abstract their specific use cases out to be able to help solve those problems. They didn't start by saying, hey, we have this really detailed GNSS processing that we need to solve. It was, let's look at the IoT ingestion problem. Let's look at the stream processing problem. And by doing that, they're able to find those purpose-built solutions that are available within AWS to solve those problems. So, that high throughput real-time stream processing, looking at MSK as that solution. Taking ECS as their independently scalable compute needs that can be fully segmented off and act as their own entire workers, using ECS for that. Doing the same thing with all of these different monitoring tools, taking advantage of things like the managed Prometheus and managed Grafana to offload a lot of the heavy lifting that would be involved to stand that up and manage it all of themselves. Taking advantage of that managed service takes off that burden and allows them to just drop it in, like Alex was talking about, into their full architecture and take advantage of what the service provides. Same thing with TimeStream, like as we were saying. It's that finding the purpose-built solution, the right tool for the right job, dropping it in and leveraging it and taking advantage of it, and then moving on to the next problem. If you were paying attention and if you've been with AWS before, you've noticed that a lot of these services that Alex was mentioning are all serverless services. This was really critical in those early days of experimentation and starting small, in that by being able to use serverless where there's no upfront provisioning of infrastructure, it's all pay as you go and pay for what exactly you're using, it enables that really quick iterative and experimentation cycle where they're able to spin up a new project, a new experiment, and see if it's going to meet their needs. And if it does, fantastic, they can scale it up. But if it doesn't meet their need, the cost of failure of doing that experiment is extremely small, because with serverless, I'm not paying for a bunch of servers up front. I'm just using the Fargate task that was used for the proof of concept. I'm only using a small bit of MSK for whatever amount of data I'm pushing through it. All of this was able to give them that foundation to freely experiment, freely try things out, and fail fast on things that didn't work, and scale up fast for things that did. And I want to give one quick caveat to that, or I guess continuation of that, where early on, EarthScope was using MSK serverless, that provisioning methodology for all of these experiments. But as they grew to a production workload and they were able to find that steady state of, the number of stations that they have doesn't change overnight. they're not having a massive swing in how much data is coming into the pipeline. They're able to then find a steady state and know, hey, we can actually have this on a provisioned Kafka cluster that we can maintain and have really good boundaries around what is going to be the throughput going into it, and are able to find some cost savings from that. So there's actually a transition here from, serverless is really good for a lot of different things, but it might not be perfect all the time for your long-term workloads. And so finding that balance between, what your workload needs and what it can support is really critical. Maybe you'll be on serverless for the entire time, and that's great. Or maybe you can find some cost savings by switching over to a provision model, whatever's going to make sense. But that all of that comes from that experimentation and some of the observability that they're able to put in place to track and know that, yes, we can have this steady state workflow. Getting into some of the more non-technical things or the organizational mindset things that EarthScope has done to have this journey from pretty much nothing on AWS 3 years ago to what they have today with everything that Alex talked about is following the pillars of the well-architected framework. And if you aren't familiar with the well-architected framework, this is a framework that AWS has put forward over all of our years of running cloud workloads and helping our customers build really strong and resilient workloads to really improve and know where are ways that we can build very good architectures. And so this is based upon 6 different pillars. The first of which being operational excellence, the ability to run your workload and produce stable and efficient systems over time. Security, having very highly secure applications and meeting all of your compliance and regulatory requirements and meeting all of those needs. Reliability, having your workload be resilient, highly available, and scalable. Performance efficiency, meeting those performance targets like a near real-time system for all of this GNSS processing. Cost optimization, making sure that the workload that you're running isn't breaking the bank. And sustainability, being able to lower the environmental impact of the workloads that you're running. The well-architected framework is a really great starting point for what does intelligent design look like in AWS, taking advantage of all of our cloud-native design methodologies, and how can we look at the applications that we're building to hit these 6 pillars in order to build very strong applications. And with EarthScope, we did a well-architected framework review. So going through all of those 6 pillars and evaluating the design of this real-time processing engine and taking a look at what can it mean to make it more reliable or more secure or more cost efficient. And by doing this review, EarthScope can see a couple of different benefits. One, being able to find ways to deploy and build faster. So looking at that ECS methodology, that came out of this review of saying, if we are able to segment our tasks and the different pieces of the processing engine into separate ECS tasks, we're able to find ways to enable our developers to have that consistent development experience and work independently of each other. The team that's working on the ingest task doesn't have to worry about what's happening with the archival team, right? And that came out of the review. Things like lowering and mitigating any kind of risk, part of the review process is a tiered list of different insights into each of these pillars. So saying this is a high impact risk or low impact risk. Having that readout of what are the low-hanging fruit that could have a very high impact in making your application more secure or more sustainable, and that prioritization is really important for knowing what should be put in our backlog and what should we focus on first for making our application better. And that goes in the same thing of making more informed decisions about changes to the architecture. Having that prioritization makes it so that you're able to really choose what's going to have the most impact. And throughout the entire process, learning more about AWS best practices and take learnings from other customers, from other SAs, and implement that into the solution. And so, in addition to all of these technical things that Alex has talked about in the well-architected framework, there's more to how you interact with AWS than just going through the console and launching a service. There's a lot of the people aspect that EarthScope was able to take advantage of to meet some of these needs. starting with the AWS account team. So as I mentioned, I'm a solutions architect. I worked with EarthScope for the past couple of years, but there's myself, there's an account manager, there's a technical account manager. Being able to leverage all of us and all of the teams behind us to bring to bear more specialization, more programs that can help EarthScope further their needs. Being able to have that open communication between us and EarthScope has been huge. And so if you don't know, you in the audience, if you don't know your AWS account manager, I'll have a QR code for you in the next slide. Please reach out to your account manager, use the QR code, and have that conversation, have that relationship with us, because we will be able to find services like TimeStream that Alex talked about that we're able to drop in and be extremely valuable. Anything like that is going to go a long way in helping you really accelerate that building and that journey with AWS. Next, there are all of our partners. So EarthScope leveraged AWS professional services early on to help kind of kickstart that development. And then Alex talked about partnering with 2i2c to build a Jupyter hub for all of their researchers to come in and build as well. Leveraging the entire partner network can go a long way in finding specialized skill sets that can really complement your own organization and, again, accelerate that journey into treating your mission, addressing your mission goals, and getting that out as fast as possible. And then finally, executive leadership. Having top-down guidance and top-down vision on what can be possible in the new realm. Stuff like the full archive analysis and making 2 petabytes worth of data immediately available to all researchers. That kind of drive is really critical in making sure that your organization keeps those big mission goals and big mission wins at the forefront of all of this work. Sometimes you can get bogged down in all of the weeds going through some of this stuff, but keeping that real big mission goal at the forefront is going to be so critical to keeping everyone kind of moving in the same direction and having a really good mission goal. And so with that, I want to leave you with some next steps. First, if you want to learn more about EarthScope, what they do and how they do it, please visit the website, and Alex and I will be here once we're done to answer any questions that you may have about what we've talked about today. If you want to learn more about what other nonprofits are doing on AWS, there's one more breakout session this week, tomorrow. Here's the information for that. We also have builder sessions and workshops tomorrow that you can attend, all within the impact track. And then, like I said, if you do not know your account manager, please, please, please scan this QR code, get in touch with them. That's going to make such a huge difference in how you are approaching how to use AWS, and we are really eager to help you build the best thing you can build. And so with that, thank you very much for being here. I know it's late, so I don't want to keep you any longer. Please fill out your surveys. It means a lot to us, and we want to keep building great content for you. And so with that, thank you so very much. If you have any questions, we'll be here.